All right, thank you for that introduction. I'd like to give a special round of thanks to the organizers of this workshop. They made some last-minute arrangements to enable me to attend. And so the reason for that is I have a 4-week-old at home. And so I was actually watching a lot of the talks earlier this week when I wasn't here with him in my arms. And he really enjoyed them, actually. So he actually laughed out loud at a couple of the appropriate jokes. And this is also a plug for watching the Simon's talks online. They are just fantastic. So it might even be better than being here because you can have more comfortable chairs. If you're stuck at home, it's not at all an impediment to taking advantage of all of the talks that they offer here. What we're going to talk to today is a lot of the stuff, or is a variation on a lot of the stuff that you guys have seen in the rest of the workshop. So we're going to talk about graph diffusions. And what the heck do I mean by a graph diffusion? This is not meant to introduce you to the topic. It's meant to introduce you to my notation on the topic, because it's slightly different than a lot of what other people have talked about. In particular, there's one sharp difference. But what we're really doing is we're taking some type of graph structure here, and we have some nodes that have some information on them, and we're letting them sort of flow around the graph or diffuse throughout the graph. And I don't want to be overly particular about the type of diffusion, because we'll look at one in particular that I'll define. But really what we're doing is we're looking at some series of this form. So a diffusion is an expansion in powers of a transition matrix P. And so this is where the difference comes in. I define my transition matrix to be column stochastic. So if you're used to probability, you will undoubtedly be used to row stochastic transition matrices, because that's how they always do them. For whatever reason, in linear algebra, we like column vectors, and so I do column stochastic transition matrices. So I wish I had a mirror that I could put up here to flip all of this stuff and make it easier for the different sides of the room to see, but it's column stochastic here. And so all of these diffusions have some notion of a seed that's starting the diffusion. So in that case, this is these two pin nodes here. And these things are used all over the place. So we'll see a couple of them, but they're used for attribute prediction. There's a problem called community detection that's very common in applied data, where you want to take a graph and divide it up into different groups that have some type of meaning internally. It's used in ranking, so Google's PageRank is a common example here, one that we'll see more about, and then finding small conductance sets. So one other thing I want to mention here, all graphs in this talk are going to be undirected graphs. So a lot of times these ideas are used with directed. Everything I'm going to say, just assume a connected, undirected graph. It could have weights, however. Yes?
Are you saying that for simplicity, or are you saying that because some of the things won't work for directed?
Some of the things won't work for directed graphs. Okay, so one specific diffusion we're going to spend a while looking at is the PageRank diffusion. So this is what Google was made famous for, or what they famously used to rank web pages. It's since been used in hundreds of other applications and found to be a very successful way of just spreading information around the graph. I'm calling these practical here because they're ones that I at least have references of a lot of different applications of where they're used. So the PageRank diffusion has some expansion in beta, and so you weight paths of length k by a value of beta to the k. The nice thing about this one and the heat kernel is they always converge, and they converge quickly, so you don't really need to take these powers up to infinity here. You can truncate them at some reasonable number, say 10, 50, 100 maybe. You don't need the full expansion to get good accuracy in practice. So a lot of these diffusions actually tie in with a lot of other ideas that were talked about earlier in the week, so you can interpret them as sort of Markov chains with some type of hitting state or stopping state. There's a nice interpretation of PageRank in terms of that, but it's not really relevant for this talk. What I want to talk about here is a particular type of localization that a lot of these solutions have. So if you take these diffusions and run them on real-world graphs, you oftentimes see results like this. So here I've got a graph that's approximately 800,000 nodes. This is a graph of the Flickr social network. And what I've done is I've taken one node of that graph and said, where does information from this one node diffuse to the rest of the graph? And so I solve this linear system. I just solve this in MATLAB, and then I plot the vector. And so when I plot this, I get 1, 2, 3, 4, maybe 5, 6, 7, 8, 9, 10, 11, 12, 13, maybe 14. I can't tell if that's the 8 or not. There's only a few large elements here if you just plot this as a vector. I generally don't like looking at it this way though. I like looking at this picture instead, which is where I've taken this vector, I've sorted it, and now I'm looking at the error I get in an approximation by taking only the largest k entries here. So if I take the 100 largest entries of this vector and look at the error in an infinity norm and a degree-weighted infinity norm, then the 100 largest entries give me an error of approximately 10 to the minus 8. So all of the remaining entries of that vector are below 10 to the minus 8. And lo and behold, I see that there's about 15 sort of significant entries of that vector. So there's this sharp drop off here where there's a big change in the scores of these vectors. And so these are what we're going to call localized vectors for this talk. What we're going to do is try and exploit them for a couple of different purposes. So our mission is to understand how localization of these vectors can help make some of these diffusions robust to graph constructions and label mistakes, and actually make things faster too. So you sort of get to have your cake and eat it as well. All right, now if you've seen me give another talk, there is a different notion of localization I've talked about in the past, and so I wanted to distinguish what I'm talking about here from that other notion. I don't know if there's a better name for this, but I just called it uniform or strong, which is where you're looking for a vector x that approximates the true solution in something like a 1 norm to an accuracy of epsilon. This is a really strict notion of localization. You get a global approximation from a small number of entries. What we're doing in this talk is an entry-wise version. And it's actually degree weighted. So the degree weighting makes a lot of the proofs and the runtime results much easier to do. We're not going to get into a ton of those here, but it turns out that this suffices for a lot of results about cuts in communities. So you don't need a whole lot of accuracy in these vectors. But this is a much weaker notion of localization than that uniform notion. So why should you keep paying attention to my talk? If you aren't interested in any of this stuff, you're welcome to either exit or fall asleep or work on your own talk or some other paper. I guess there's a stock deadline coming up. So I'm going to talk about a new interpretation for the PageRank diffusion in terms of an approximation of a min-cut problem. So we saw a talk earlier this morning about how min-cuts has to do with conductance and how you can solve these parametric flow problems. There's a really neat construction that shows exactly how you get this PageRank diffusion out of a min-cut problem. There's also a really efficient algorithm called the PageRank push algorithm that gives you an approximation to the PageRank diffusion that gives you that entry-wise localization. What we're going to show is that algorithm actually exactly solves, and when I say exactly, I mean 16 digits of accuracy. It solves a 1 norm regularized version of the PageRank diffusion. So if you like the output of that algorithm, you like the output of that algorithm because it gives you this really particular type of PageRank approximation. What we're going to do is we're going to use these two insights, or use these two as sort of primitives to look at different types of diffusions used in semi-supervised learning and give a little bit of guidance on how you can make them slightly more robust. So I'll explain. There's a statistical notion of robustness, and what I really mean here is robustness in the sense of if you gave these to a somewhat uninformed user and had them run them, we'll see cases where if you sort of looked at the textbook algorithm, you'd get horribly wrong answers. But there's like a trivial tweak you can make to get much better answers. And so we'll go through a couple of those. All right, so just a little bit of background. We're looking at PageRank here on undirected graphs. A lot of people think this is very strange. So a Markov chain on an undirected graph has a unique a uniform random walk on an undirected graph has this well-known stationary distribution that's proportional to the degree of every node. However, the PageRank random walk is a particular random walk. With probability beta, we take one of those standard random walk steps, but then with probability 1 minus beta, we jump back according to some seed distribution S. For this talk, think of S as just a single node or just a few nodes somewhere in your graph. These jumps mean that your Markov chain is no longer reversible, so you no longer have a simple, trivial stationary distribution of these PageRank random walks, even on an undirected graph. And actually, a great open question would be to sort of quantify the effect of this. I've never seen a good quantification of how much you can tweak the stationary distribution with these random jumps. Empirically, it's a lot. Unless, actually, this is the stationary distribution of your random walk, in which case you don't change anything. But that's a sort of technical aside. If you have an undirected graph, then you can either compute the PageRank distribution X by solving a linear system with the transition matrix, so AD inverse was the transition matrix, or you can turn it into a problem on the combinatorial Laplacian matrix. So there was a talk by Bin Yu on Monday talking about different versions, different regularized versions of spectral clustering. There they were adding components to the Laplacian matrix. Here what we're doing is we're bulking up the degree of the Laplacian matrix. So if alpha were 0 here, you'd end up with a singular Laplacian system. But if you just add a little bit of extra weight on the diagonal, you get a non-singular system that's equivalent up to a degree scaling of solving a PageRank system. Yes?
So when you say jump randomly from distribution S, you just sample from the distribution.
Sample from the distribution S and just update where you are, exactly. And think of S as really just one node, so you sort of always go back to where you started in the graph. Okay, I said we'd relate this back to min-cut problems. So this is a review of the ST min-cut problem. We're given a graph. We're given two special nodes, S and T. What we want to do is we want to find the best way of splitting up this graph where S is on one side and T is on the other side that cuts the fewest number of edges. So you can state this as a linear program with the incidence matrix of the graph. And what we're doing here is we're writing it with the unweighted incidence matrix and using the capacities or the weights on the edges as a weighted norm. So a lot of people would have stuck the C inside to form some sort of weighted incidence matrix. Here, the incidence matrix is staying unweighted. The weights are going in the norms. This is just a notational thing that makes it a little bit easier. So this is really what we mean by that notation. And this is a linear program. If it were unweighted, you can solve this via max flow problem. If it's weighted, you either need a capacitated max flow solver, or you can just use a network simplex solver, or even just an industrial LP package. They tend to work incredibly well on these problems. In order to relate PageRank to min-cut, we're going to have to introduce a construction that I've called the localized cut graph. It's related to a construction used in a paper called that describes a primitive called flow improved by Reed Anderson and Kevin Lang from SOTA 2007, and more recently a construction by Lorenzo Recchia and Zhu that was about localized flow methods. The idea here is we're going to take our original graph, we're going to introduce two new nodes, S and T, so standard so far, but we're going to connect node S to all nodes in the subset S with weight alpha times the degree of those nodes. And we're going to connect the vertex T to all nodes in S bar with weight alpha times their degree. So in terms of PageRank, think of S as giving you some measure of that distribution there. So this gives us a new incidence matrix that now depends on S. And so the ST min-cut problem here is just to minimize this one norm objective subject to the cut constraints there. In order to get PageRank, we get the world's simplest slide transition. We take this problem here and we turn it into an electrical flow problem. So we take that 1 and make it into a 2. So again, if you missed that, we take the ST min cut problem, and we take that 1 and make it into a 2. So this is now a 2-norm optimization problem, or a spectral optimization problem. And if you set up all the constants right, the PageRank vector that satisfies that linear equation is up to scaling by some volume that depends on the size of your set. The solution of this this convex optimization problem here. So again, PageRank is really just a spectral relaxation of a particular ST min cut construction. How do you prove this? You just square the objective, apply your constraints, and it's easy. Yes?
So the min cut formulation is in the 2-norm or 1-norm?
So the min cut is in the 1-norm. So then you have to relax to the electrical flow, or the spectral min cut. But you take the construction from the 1-norm and you just approximate it with a 2-norm, and you would have gotten PageRank. Again, this is on this particular construction here, so it's not on a general one. All right, so that worked for a very particular setup. That is, I said, there's a set S that gives rise to a PageRank problem. Turns out the converse holds as well, so you can take any PageRank problem and construct the set S. You just need a slight generalization. So when I had our set S before, you connected it with weight degree leading to every node if it was in that set, and then if it was outside that set, you had degree leading to T. If you have a general vector, or just the simplest case is the uniform form vector, what you do is you connect every node in S to all nodes in your graph with weight alpha. You connect them to node T with degree minus 1 times alpha. So the idea here is that the total degree you're adding to each node of the graph has to be alpha. So at every node you're adding alpha times the degree of that node to its local weight. This is why you get the alpha D in the Laplacian term. Okay, so I hadn't ever seen it written as cleanly as this before, but I'm not sure this would have surprised anyone who is really familiar with these things, although it is nice to have it written out explicitly. But PageRank is really it's implicitly approximating a solution of these ST min cut problems, and at least now I have a much better explanation for why PageRank shows up in all of these cuts and small conductance problems when I have to answer students about it. But I claim there's a couple of other insights we can draw from this. So this same idea holds for a variety of other diffusions used in semi-supervised learning as well. So let me just go through a couple of these other constructions. There was a paper by Zhao et al. In 2003 that described a different technique with the Laplacian, and what they're doing is they're taking your seed set S and connecting it with weight alpha 1. So they're not doing a degree-weighted version when you're linking to your seed set, but then they're still weighting all connections to T such that the total weight you're adding is alpha times D. I've called the PageRank one the Anderson-Lang construction just because they were one of the first ones to describe something close. There's others by Thorsten at Cornell and some of the authors in the room here, where you ignore all the intermediate nodes and just use some additional label information and or explicitly pin the nodes to particular sides of the set. But again, once you have all of these flow problems, you get a spectral diffusion just by taking the min cut problem and relaxing it to a 2. So a lot of what I'm going to say in the second part, I'll talk about in terms of PageRank, but different variations on those same ideas apply to a couple of these other ones as well. So what we're going to do now is study a particular algorithm to compute an approximation of the PageRank diffusion very quickly. This is what's called the push algorithm for PageRank. So the push algorithm for PageRank was proposed in the form that's most close to what I have by Anderson, Chung, and Lang in their 2005 stock paper. It's actually proposed even, a variation of it was proposed by Frank McSherry, Jay Weedham, and Pavel Birkin in a couple of different papers. And actually it's really just a special case of a linear solver that goes back to Gauss, so we'll see that as well. But why did they propose it in the Anderson, Chung, and Lang paper and what were their customizations. I'll describe those shortly, but they were using it to derive an improved runtime result for some of these balanced solvers that people look at. But empirically, it's been used in a whole lot of different studies of communities of networks. So if you want to do community detection on networks, this is actually one of the most accurate methods of doing it. And so when I say accurate, it shows up in study after study after study as one of the ones that gives you really good communities in practice. Why is this? This is, in some sense, a great question, but in a lot of studies this happens. You can also show a local Cheeger inequality about this particular, or you can use the output of this algorithm to show a local Cheeger inequality, which relates the set that you get back to the set of best conductance that contains your seed nodes. A lot of people just use it because they want some quick, dirty, and cheap approximation to a PageRank vector. So in particular, I would have no problem running this on a graph with 4 billion edges on my laptop. It doesn't need to explore the majority of the graph in order to give you this type of approximation to PageRank, and so you can use it on just massive problems very quickly. And the reason it does that is it gives you these nice weakly localized or entry-wise localized solutions of PageRank. So what I'm doing here, this will reset in a second. This algorithm depends on an accuracy parameter epsilon, and what I'm showing you is how the solution of these PageRank vectors, these epsilon accurate PageRank vectors, vary with epsilon. And so what you can see here is it starts from these seed nodes. Any node that's small is actually exactly 0 in the solution. So the PageRank vector is in general dense. It's got a full set of non-zeros, but the output from this algorithm only returns a very small number for reasonable parameters epsilon. So it doesn't have to look at the entire graph. It's able to find these just by doing some local exploration around the seed nodes. And so you can see how as we get more and more accurate answers, it has to fill in more and more of the graph. How would you use this in practice? What you would do is probably do some type of bisection search where you're looking for sets of something like a quarter of the graph or a tenth of the graph. So if you find that it's becoming too dense, you'd reduce your value of epsilon down and just stop that search there. So you can bound the amount of work it does in terms of epsilon and this parameter beta in PageRank, so it gives you an epsilon accurate solution, this entry-wise sense, in 1 over epsilon times 1 over beta work. The push algorithm, I'll describe in a second, is closely related to the Gauss-Seidel and Gauss-Southwell methods for solving a linear system of equations. So for this slide, we're going to look at just a system of equations. AX is equal to B, so A is any matrix here, and B is any right-hand side. Both of these algorithms work in a coordinate-wise updating fashion. So what they do is they say pick a coordinate j of your solution and update that coordinate j such that you exactly solve the jth equation of your system. Okay, so all they're doing is they're picking a coordinate and just being greedy on that coordinate, saying, hey, I can change x sub j, so I'm going to change x sub j to ensure that I satisfy this. So in words, what they're doing is they're relaxing or freeing the jth coordinate and then exactly satisfying the equation in that one. How do you choose the coordinate j? Well, Gauss-Seidel, as it's usually explained in a textbook, is you start at equation 1, and then you cycle all the way through all the equations, 1 down to j, and that's one iteration of Gauss-Seidel on the entire matrix. And then you would repeat this over and over again. So you go 1 through j, 1 through j, 1 through j, 1 through j. Gauss-Southwell is a little bit smarter. It says, hey, there's this notion of residual which says how much my equations failed to be satisfied. So the residual is sort of how much error I have, or it's proportional to how much error. Gauss-Southwell says, look at the largest component in the residual and update that equation. So I make the largest residual 0. So note that after I solve this exactly, that jth component of the residual becomes 0. So it's sort of like squashing your residual all over the graph. And now every time you squash it in one component, it changes elsewhere in your graph. And so this is, in some sense, the origin of the name push. So you can use 2 different ideas to implement these things on a graph, which would be called PageRank push and PageRank pull, respectively. So you could use PageRank pull if you had an undirected graph and you had access to the in degrees, which are really the out degrees. But in PageRank pull, what you'd do is you'd say, well, hey, the PageRank equation, I've switched to using alpha here. I apologize. These were a series of old animated slides, and so I didn't want to muck up the animations just to switch alpha to beta. So I should be writing beta here, but I apologize. I think most people can get it. What you're doing is the PageRank value at your node depends on your incoming ones, and so all we do is we just update that one to be the average of our incoming neighbors. And so this is PageRank poll, which is satisfying that equation locally in terms of that row of the PageRank equation. I said all graphs were undirected. If you did have a directed graph, sometimes it can be annoying to access in degrees of that graph. And so there's a way of rewriting this, which is called the PageRank push algorithm, where you do the same thing, but you explicitly maintain a residual vector. So now when you update the jth equation here, what happens is I add the component of the residual, which for PageRank you can show exactly cancels out my current term. But then I change this equation, and so I change the residual on all nodes that I link to. So nodes X, nodes A, B, and C have their residual changed. And so what happens is I change my equation by adding in the residual. I update my residual to be 0, but then I have to change all of my neighbors' residuals by some amount that's proportional to how much I got changed. So this is the way it's usually done in the PageRank push algorithm, because you maintain an explicit solution vector and the residual vector. And using the residual vector sort of allows you to see how far off you are. In this one, you don't need a residual vector, so it saves memory on the computer, but it doesn't ever allow you to sort of see where you might like to operate on your vector. So now there's one more trick that makes the push method work. And this is in some sense the key insight here. So the push method, as it's used in Anderson's work, starts out with a solution that's 0. The residual is just the right-hand side of the PageRank system. And we have iteration 1. So while any component of the residual is larger than epsilon, so that is while we're at least epsilon away times the degree, what we're going to do is we're going to change that component, but we're not going to take the step that makes that component of the residual exactly 0. We're going to take a step that makes the residual exactly equal to epsilon times d, or in general there's a parameter rho we get that says how much you're going to be between epsilon d and 0. So if rho were 0, then you'd take the step that makes, or that's exactly equal to rj. If rho is 1, then you exactly satisfy that constraint there. And then you update the remaining residual for all adjacent nodes, and you leave everything else untouched. And that's the push method. So the key insight here is, one, you only have to operate on entries that are large enough, and you can maintain those in a queue, so you don't have to maintain any very expensive data structures here. The second thing is that you step to, or you take in some sense the smallest step possible that will allow you to stop considering this method or that node again in the future. And then you just keep working through it. Okay, now here's the magic. If you run that algorithm, you exactly solve this convex optimization problem here. So how does this relate back to the min-cut version we saw before? So the C and the 2 here are the same. So this is again the, I think I might have had X before. It turns out you have to square the objective when you look you look at it this way. In the other case, you could have squared or unsquared the objective. That was fine. Here, you need the square there in the objective. The impact of that parameter epsilon gives you a number kappa here. So, oh, sorry, I should have changed from epsilon to tau. So tau and epsilon are the same on the previous slides. So epsilon was the accuracy, and epsilon is equal to tau. So this parameter kappa, or how much you regularize, or how much you approximate the solution, gives you how much of a one-norm penalty there is on your answer. And then you have the same types of constraints here. So this is really cool because it sort of explains why the heck the answers from this thing are sparse. For approximate solutions of PageRank, there's no guarantee that they should be sparse at all. This entire solution is dense, there are a whole host of epsilon accurate answers out there to a set of PageRank linear equations. What's the set that the push method gives you that's been so useful in practice? Well, it's exactly related to this one norm optimization problem, and it's sort of redundant to say now, but in general, if you have a one norm, it tends to encourage sparsity. So I'm not making a precise statement about it here, I'm just sort of relying on that. But the algorithmic complexity then gives you sparsity explicitly. So this explains, amongst all the epsilon approximate vectors, why this method or why this algorithm finds these sparse ones, which is really nice because you can do the same type of regularization on the other method or on the other diffusions as well, and you can probably make them a little bit faster in practice, which is one of the key challenges with using them in practice. How do you prove something like this? You write out the KKT conditions and then sit and stare at them in a coffee shop for a very long time, and then come back the next day, and then the next day, and then after a while you say, oh my gosh, that's so simple, how did I miss that? So again, once you write it down, there's nothing left to do, but I don't know how to tell you to come up with that other than staring at it for a very long time. But this is really cool. So the PageRank push method implicitly solves a one-norm regularized two-norm cut approximation. But more importantly, when we're solving PageRank push, we had this tolerance parameter epsilon. And so when we're solving PageRank, push gives us a really crappy solution. It's not a good approximation of PageRank, but it gives us a perfectly accurate answer to this other problem. So if you say these approximations for community detection are really good, now you can look at this other problem and look at better algorithms to approximate it instead of different types of approximations of PageRank in the first place. And there's actually yet another insight, which is that these regularized diffusions should, in some sense, be more robust in data applications. And so this is the starting point for the third piece of the talk. They're definitely faster to compute. These push algorithms run really quickly, whereas computing entire PageRank vectors tends to be quite a bit more slow. So again, all we're doing here is just adding a one norm regularization term onto these two norm diffusions. So to study that, we're going to look at semi-supervised and or diffusion-based learning. And so the idea here is we're given a graph, and we're giving some set of labels on the different nodes of this graph. So here, the canonical example of this is the digits data set. So you've got a graph between all the digits, and you know that this node here is a 1, this node's a 2, this node's a 3, and a 4. And the problem is to figure out what the other nodes of this graph are in terms of the digits. And so there's a whole bunch of different algorithms for this, but there was those four we talked about initially, all based on diffusion, where what you do is you run a diffusion for each label. So you say, I want to run a diffusion for label 1. This gives me some information over the entire graph related to node 1. I run a diffusion for label 2. This gives me some information. And then you assign labels based on the results of those diffusions. So we did this, and we cooked up a really simple graph here. So here is a graph with 3 different classes. So class 1, 2, and 3. Class 2 is a little bit smaller. And what we did is we took 2 standard diffusions, so Zhao and the Anderson-Lang. There's actually a couple more pictures off here that look the same, but if I got them all on the slide, no one could read it. So trust me when I say they look the same. If you don't believe me, I'm happy to show you afterwards. When we looked at these with 3 labels, things looked pretty good. So for class 1, the diffusion you get is this blue vector here, and how should you read this? Well, the blue vector, we're looking at the weight on every node of the graph, and they're ordered by their different classes. And so you see the blue vector is high on class 1 and low on class 2 and 3. The red vector is high on class 3 and low in class 2 and 1. When you try this with the Anderson-Lang, you notice something strange. If you run this diffusion, you see that class 1 is high everywhere. Class 3 is lower than class 1, and class 2 is lower than class 1, except for those single nodes that you chose as your seeds of your diffusion. So you say, well, maybe we need more classes or something like this. If you do Zhao with 15 labels, you see basically the same thing. the diffusion for class 1 dominates, and you see the same thing with Anderson-Lang. The diffusion for class 1 continues to dominate. Now this is when, as experienced people with these diffusions, you guys would say, well, of course this is what happens. Class 1 is bigger, so when you sample more, you're just increasing the value of that diffusion there. But what you would do if you just followed the standard algorithm in all the papers is you would take these results here and predict class 1 as the label for all of these different cases. And that's ridiculous. So if you just implemented the standard algorithm without understanding these diffusions, you would get the wrong answer. And you might say, okay, maybe you've constructed this. We did this on the digits problem. And so if you just use the standard algorithm and you look at the error rate, if you look at the average number of training cases per class, so this is on the digits data set, and this is with a couple of different diffusions here, the error rate you get is 0.9. So what happens is you're always predicting one class of your data set. So it's not just the it's not that particular data set. This actually shows up in a variety of cases. I'll come back to what these two are in a second, but this is what happens. So these two, sorry, I guess I'll say it now. These two lines are what you get if you regularize your diffusions. So if you add that one norm regularization in, you actually get much better answers here. And initially when we saw this, we were misled into thinking our regularization actually helped things. It turns out we're both looking at the problem wrong. So how much time do I have? Okay, good. In some sense, the title of this seminar is Unifying Theory and Practice, and I claim that we made a very fundamental error when we were attempting to look at those values of the diffusion in order to do the class labels. So remember insight 1. Diffusions are all approximations to cuts. All right, so when we approximate a cut, or when we approximate an eigenvector, how do we take that eigenvector and round it back to an actual cut of our graph? Well, there's the standard algorithm which says you take the zero splitting of that. But that's not a very good algorithm in practice, and in fact the Cheeger inequality doesn't apply to that cut. The Cheeger inequality applies to the sweep cut, where you go through all partitions induced by the ordering. And so the way to fix this is really simple. If you look at this result here for Anderson and Lang with three labels, if you just look at the ordering induced by these three vectors, you'll get the answer right in almost all cases. So from class 2, although the value of the class 2 diffusion is smaller than the class 1 diffusion, this node is the second highest in the rank of the class 2 diffusion, whereas it's well below all of these others in the class 1 diffusion. And so the idea is you just use the rank of these entries in the vector, so that their value, in order to round. So what happens, so in other words, we sweep over all cuts from these approximate ones, but we just use the rank of the vector in the sorted entry instead. So when you do this on digits, here's what you get with the sort of off-the-shelf textbook algorithm, which gives you disastrously bad results. If you just do rank rounding, you get exactly what you expect. So first of all, you get nice error that decreases as you add more as you add more labels. Somewhat to our chagrin, it turns out that regularization has almost no impact on this anymore. So whether or not you regularize, you would be doing that purely for speed and not for any type of improved performance, which is what we were hoping for a little bit there. So the only difference between these two is how you round the labels. So this one's based on rank, and that one's based on value. Yes?
So I was wondering if you could go back to the previous slide. I was wondering, what if, like, I treat the three things not as, don't look at their rank, but just treat them as three coordinates in
Okay.
three space and map there, and I just do clustering there. That's like spectral clustering type of thing. Would that work?
So the problem is, how do you take advantage? So you're saying ignore the fact that we sort of pick these with our labeled points, just cluster them, right?
No. So I guess each vertical column is for one original data point.
Yeah.
Now if I treat the value of three colors as coordinates, right, represent my point in that free space.
So, but then how do you turn that into a label?
with the regression.
So you do regression on the labels. So now I remember thinking about this and had some good example for why that doesn't help you in this case, and now it's failing me. So that's an excellent question. Let me think about it again and try and remember that. So let's talk after the talk, and I convinced myself that that didn't help. So suffice it to say, I still think that rank-based rounding is a much simpler thing that you can do here that just totally fixes the problem. But there's one other point I wanted to make in the 5 minutes I have left.
So can you just say, when you say rank, what exactly?
So what I mean by rank is, this is the node with rank 1 in diffusion 1. This is I think this is rank 2, this is rank 3, 4, 5, 6. So just list them by their orders, and then take the nodes with, so now we have a new set of information, which is the order of every node in the diffusion, and say, oh, I want to find the diffusion where it's the highest ranked, instead of the highest value.
Wait, but how do you decide? You have 3 different rankings, right?
Mm-hmm.
How do you
So,
decide which one belongs to which?
So this one, this node here is rank 2 in class 2, and it's rank 52 in class 1, and probably rank 23 or something in class 3.
Oh, okay.
So I'd choose the maximum of those.
Okay.
So in MATLAB, this is almost embarrassingly simple. You just call sort on the vector, and then you call max. So instead of calling max initially, you call sort first and then call max. Yes?
Yeah, so you have, I guess, error percentages. Do you have any sense of whether the error is larger in like the large classes or how it's distributed?
That's an excellent question. I wish I had those statistics off the top of my head, but no, I don't. When we looked at the digits, I mean, you do see that it's largest in the largest class. So it always predicts that class and just gets everything else wrong. So the intuition that it's worst in the largest classes is right. So if you knew the class sizes up front, you could probably normalize things in a way that avoids this. But you don't have to do that. You can just use the rank instead. So our point here is that if you were packaging this up, you would probably want to use rank instead of the value and all of these other ideas, because it'll give you something that's pretty much as close, but it's just a lot simpler. So now, I cheated when I was explaining semi-supervised learning. I said that we're given a graph, and this is not true. We're given data, usually, in a semi-supervised learning problem with a few labeled points, and we want to predict the label and the rest of the data. And so step 0 of this algorithm is actually create a graph from our set of points. And so when we do this semi-supervised learning on graphs, what we usually do is use some type of distance function between nodes. And there's a parameter here, which is a variance or a kernel width per parameter is the right way of thinking about it. So if you know the answers, or if you have some time to do some experimentation, you can cross-validate over these. But what we want to understand is it sparse graphs or dense graphs where these things matter more? So in some sense, people like sparse graphs because they're easier to work with. But are those the best things that you can do in terms of the data? So we wanted to see, where does this regularization in terms of the one norm term on PageRank actually help more? Does it help more with dense graphs or sparse graphs? All right, do we have time for a quick poll? Can I just see if people think it'll help more with sparse graphs or dense graphs? Sparse graphs. Okay, dense graphs. Okay, I thought it would help more with dense graphs. And I was totally wrong. It helps more with sparse graphs. And so we did some additional study to investigate why. So what we're looking at here is how much regularization matters for a wide kernel width or a dense graph. And it doesn't matter at all if your graph is dense. This is just like a non-issue. If your graph is sparse, it actually does improve your performance a little bit, just a little bit. So I don't want to make too much of a deal about these, but I was really sort of shocked about this. I wanted to understand it a little bit more.
For the dense graph, do you need to penalize more? Like
So excellent question. So do you need to penalize more? And the answer is no. So if you penalize a dense graph more, what happens is you get worse results. And I'll give a little bit of intuition for this. We're trying to pin some of these things down in theory. We don't have the statements nailed down yet. But intuitively, if you regularize too much, you regularize your entire solution away. So there's some natural notion of regularization that gives you the right answer, and if you're below that, you get the wrong answer, and if you're above that, it doesn't matter. And with the dense graph, there's basically no room there. So you either get the right answer or you get the wrong answer. So what we did is we took a really simple graph I can draw here. We have, in some sense, the motivation here is these are the correct answers we want. I've introduced one error. And here I'm looking at the value of a diffusion in this graph. So these are the answers I want to say are correct. These are what I want to say are unavoidable errors. So once you introduce that additional wrong label, you can't avoid those errors if you have a semi-supervised learning. Or you would have to have another label allow you to correct those errors. But just from one label, you can't avoid them. So what we want to do is take this graph and make it dense. So how did we do it? Just to play around with this, well, we took the sum of the k powers of the graph. So we powered up the adjacency matrix and used that as a dense representation of this graph instead. And it turns out we saw exactly the same thing. So up on the top, we have no regularization. So these are fully dense diffusions. Here we have the sparse graph. Here we have the dense graph. Here we add in regularization. So what happens on these two cases? When you run the diffusion, the full diffusion in the dense graph, you can see it actually does a pretty good job on all the correct answers, and it does a reasonable job of actually correcting the incorrect answers. And if I have to hand wave in 2 seconds and say why this is, when you densify the graph, you reinforce the manifold structure, the underlying structure of the graph. When you look at this with regularization, there's almost no difference between these two diffusions anymore. In all cases, you sort of, with the regularization or on the sparse or the dense case, you downweight all of these avoidable errors up in the upper right. And so that's hand wavy. I know this is unifying theory and practice, and my last slide is we need some theory to explain what's going on there more concretely. But I think there's a real phenomenon there. So if you want to do these diffusions more robustly in practice, so first of all, I would encourage you to use rank-based rounding. And two, if you can, actually can, it seems like denser graphs give you better answers in practice.
Could it be the case that for dense graphs it's better to get inequalities?
That's an excellent conjecture. You would know more about that than I would off the top of my head. So does anyone else know that with denser graphs have better Cheeger inequalities? Okay, I don't know that either, so excellent question. So again, if you'd like more, so there's a paper we had at ICML that talks about these relationships with PageRank, and we're trying to tie up the knot on some of those diffusion-based ideas. But that's it. Thank you.
Yeah. Say that depends on whether the power is not weighted or
So yes, could you show the avoidable error again? Like what was what was the diffusion here?
So the diffusion here is a spectral diffusion. So it's a PageRank diffusion or a Laplacian diffusion. And the idea with the avoidable errors is you want to, it doesn't show up quite as well here, but this diffusion here is actually quite large in that region. So if you do the unregularized diffusion, you actually end up with larger entries than you would like out here. Now, ideally, they're going to be corrected by a different one, but if they're not corrected enough, that's a regime where you would potentially run into problems. So again, we're trying to illustrate this result that occurs on the digits, where it's not as easy to see what's going on. But I think this motivates some sort of avenues to tackle here. So ideally, you want your diffusions to be 0 in this region.
Thanks again.
Thank you.